Hello, here's your screencast for section 4.7 to 4.9. Four point seven is on types of chemical reactions. The learning objective is identify a reaction as acid-base, oxidation, reduction, or precipitation. So you want to know what sets those three types of reactions apart from the others. So for essential knowledge, an acid-base reaction, that is shown by a transfer of a hydrogen ion. So in this case, this example right here, a hydrogen ion is being transferred from HCl over to NH3, and NH3 turns into NH4 plus, and then Cl, the chloride ion, is all that's left. In a precipitation reaction, that is when you have a solid that forms from two aqueous solutions. In this case, here's a solid barium iodide that's being formed in this reaction. And then with this, you also want to know the soluble salts, as in the ions that are always soluble, and that would be sodium, potassium, and nitrate, and ammonium. So if you have an ionic compound with any of these four ions, you can assume that they're always going to be soluble. They're going to be aqueous in solution. And then the other type is a redox reaction, and a redox reaction is defined as a reaction where you have a transfer of electrons. So this is about electrons that are being transferred. And we use oxidation numbers to show how the changes in electrons are taking place. And a redox reaction is reduction and oxidation, and they always go together. They go hand in hand. And reduction is shown as a decrease in oxidation number. In this case, we have manganese. It goes from a +4 to a +2. So manganese is being reduced. And what that really means is when something's being reduced, that means you're increasing the number of electrons. So it's gaining electrons. So reduction is defined as a gain in electrons. And on the other way is now you have oxidation. Chlorine, it's going from -1 to 0. So oxidation is an increase in the oxidation numbers, and oxidation is really defined as a loss of electrons. If you remember oil rig, to help you remember this, where you have oxidation, oil. There you go. So oxidation is a loss, reduction is a gain, and that's referring to electrons. Okay? And then you also want to know the rules for defining oxidation numbers. So I'll just read those off to you, and you can pause and record as needed. So the first thing, an element is always going to have an oxidation number of 0. A monatomic ion is always going to have an oxidation number of whatever its charge is. A compound, the oxidation numbers are going to add to 0. In a polyatomic ion, the oxidation numbers will add up to whatever the ionic charge is. And then you have oxygen is going to be -2. Hydrogen is going to be +1. And then group 1 or 2 metals is going to be their charge. So either +1 or +2. And then you can use those rules, and then you can go through and assign oxidation numbers to every element in a reaction. And then in a redox reaction, there's a change. Something is going to increase, and that's going to be what's oxidized, and something's going to decrease, and that's going to be the element that's reduced. Okay, then next you have 4.8, that's Introduction to Acid-Base Reactions. And the learning objective for this section is identify species as Bronsted-Lowry acids, bases, and/or conjugate acid-base pairs based on proton transfer involving those species. So the essential knowledge is you want to be able to identify Bronsted-Lowry acids and bases. And an acid is defined as a hydrogen ion or proton donor. So it's all about what's happening with the hydrogen ion. Now, a hydrogen ion is also called a proton. So a Bronsted-Lowry acid is whatever loses the hydrogen ion in the reaction. So in this case, sulfuric acid is losing a hydrogen to water. So it's going to be our Bronsted-Lowry acid. And then the base is whatever it's defined as a hydrogen ion or proton acceptor. So in this case, water is defined as your Bronsted-Lowry base because it's accepting that hydrogen ion from sulfuric acid. And then what happens is after that hydrogen ion is transferred, whatever is remaining after that transfer for the acid is called the conjugate base. So the acid turns into the conjugate base, and then your base turns into the conjugate acid. So if you were asked, like, what are the Bronsted-Lowry acids for this reaction, you would say sulfuric acid and the hydronium ion. It's the acid and the conjugate acid. If you were asked, well, what's the Bronsted-Lowry bases, you would say water is the base, and then the bisulfate or HSO4 negative, the conjugate base. So it's the base and the conjugate base. But then you have the conjugate acid-base pairs. Conjugate acid-base pairs are species that differ by a single hydrogen ion. And there's always two in the reaction. It's going to be the acid and the conjugate base, so H2SO4 and HSO4 negative. And it's going to be the other one's water and hydronium. So again, a conjugate acid-base pair is something that differ by a single hydrogen ion. And the last part is redox reactions. The learning objective is represent a balanced redox reaction equation using half reactions. So the essential knowledge is really just one thing. You want to be able to balance with half reactions. And there's three steps, really. So the first step is you're going to split up the redox reaction into two halves. The second step, you're going to balance. You balance each half, and it has to go in this order. You balance everything else. And everything else, I mean everything that's not oxygen or hydrogen. So any other element, you balance that first. And then you balance oxygens by adding water molecules. And then you balance hydrogen by adding hydrogen ions. And then you balance the charge by adding electrons. And I'll show you that process. We'll go through an example on the next slide. But then once each half reaction is balanced for these things, then you put the two halves back together again. So here's an example. So we have this reaction right here, and it's in an acidic solution. So the first step was to take this reaction and split it up into an oxidation half and a reduction half. So here's our two halves right there. And you want to put like species together. So this has the chlorine in it, and this has the chromium, and you just want to put those together. All right. And then the next step was to balance everything that's not oxygen or hydrogen. So in this case, we just have chlorine. So there's one chlorine here, one chlorine there. Those are equal. One chromium, those are equal. So we don't have to do anything for that step. The next step was to balance oxygens by adding water molecules. So you add water molecules to the side that has fewer oxygens to make the oxygens equal. After that, you add hydrogen ions to the side that has fewer hydrogens to make them equal. Then the last step for each half is to balance the charge. So you add electrons to the side that's more positive to make the charges equal. In this case, we have to add 2 electrons on the left for this half and 2 electrons on the right for that half. And then finally, you put the two halves together. Now, before you put the two halves together, the electrons have to cancel out. In this case, the electrons are equal. There's 2 electrons on each side. So now, since they're on opposite sides, we cancel them out. So the electrons have to cancel. Now, if they weren't equal, then you'd multiply one or both reactions by some factor to get them to a number that's equal. And then we look for like terms on opposite sides that can cancel. So we have water. There's one water here, two waters here. So the lower number is gone, and there's one water left over on the left. There's 2H plus here, 4H plus right there. So the lower number is gone, and then this is reduced down to 2. And then once we cancel everything, now whatever is left over, we put it into one reaction. So we have H2O, ClO, negative CrO2 on the reactant side, and then we have 1, 2, 3 things on the product side, and we put all those together. And that's our final balanced equation. Now, this is a long problem, and something like this, you will not have to do a problem like this from beginning to end on the AP exam. But there might be a possibility where you have to do like maybe 1 or 2 steps, like maybe a couple steps to one of the half reactions. But you're not going to have to do the whole thing, but you still have to know all the steps. All right, so that's enough for today. Have a great day. Bye.